Bonding. What holds stuff together? So we've mentioned this before, that when chemicals react, then the atoms can come together and chemical bonds can form between them. They're not just mixtures, they're actually chemically bonded, so the atoms are held together by forces. Now, the driving force behind this process is the search for stability. So atoms usually form chemical bonds to become more stable. They're looking for stability. There are some exceptions in the periodic table. You know of atoms, some of the elements, that don't react. They're very unreactive. And it's because they already have a lot of stability. So which group of elements are already very stable? Yes, it's group 0 or group 8, the noble gases. And the noble gases are very stable. Why? Because they already have a full outer shell of electrons. So this is the thing that all atoms are aiming for. They're aiming to get a full outer shell of electrons. They are electronic wannabes, and when they take part in chemical reactions, they try and achieve the noble gas electronic configuration. NGEC, abbreviated in future slides. So the idea would be that all atoms are looking for a full outer shell of electrons to achieve stability. There they are, that's the noble gases. So you can see they've got a full outer shell and they're already stable. 2 electrons, 8, 8, 8, etc. When the chemicals react, they form bonds between the atoms, between the particles that are involved. So the idea would be that in a chemical reaction, something happens to create bonds between the atoms. And those bonds can be of 3 types. They can be ionic bonds, covalent bonds, or metallic bonds. And we'll talk about each of these in turn. Let's start with ionic bonding. Now, ionic compounds form when metals on the left-hand side of the periodic table react with non-metals, which are on the right-hand side of the periodic table. The classic example you need to know is the reaction between sodium and chlorine. Now, what does sodium have to do to achieve stability? Let's look at a sodium atom. A sodium atom has 1 electron in the outer shell, and what it does, in order to achieve a noble gas electronic configuration, it loses that electron and it now has 8 electrons in its outer shell. By losing that electron, if it's got 1 fewer electrons and it's still got the same number of protons that it started with, then it now has a positive charge, a 1 positive charge, because it's lost 1 electron. So what's formed is a sodium ion. The sodium ion has the electronic configuration of 2, 8, and it has a positive charge because it's lost an electron. Now here's a definition for you. An ion is a charged particle. So something that's got a positive or a negative charge is an ion. Okay, let's have a look at chlorine. What must chlorine do to achieve a noble gas electronic configuration? So chlorine's got 7 electrons in the outer shell, and in order to gain a full outer shell, the easiest thing to do is for it to gain an electron. So now it's got 8 electrons in the outer shell. It's got 1 more electron than protons now, so it now has a net negative charge, 1 negative. And its electronic configuration is 2, 8, 8. It has become Cl-, a chloride ion. That's slightly different, isn't it? Because the ending's changed on the name there, and that's a rule. The rule is when you have a non-metal element and it forms a simple ion, it adopts the ending "ide." So chloride, oxide, nitride, bromide, etc. So they've come together. The sodium has transferred an electron to the chlorine, so it becomes a sodium ion, and a chloride ion, and transferred, that's a key word here in ionic bonding. Electrons are transferred, ions are formed, and then, because they have opposite charges, what do? Well, they attract each other. Opposite charges attract. So an ionic bond is formed. That makes sense. These diagrams are called dot and cross diagrams. As you can see, the dots and crosses involved. And the idea is it shows you where the electrons have come from and where they've gone. So here the chloride ion has got one cross from the sodium atom originally. And you can see that cross is there. So you can see that electron came from the sodium. Once lots of ions are formed and they come together in a structure, a crystal, of alternating positive and negative ions. You have sodium, Na+, Cl-, Na+, Cl-. They form this structure, this pattern, a regular arrangement of ions. And this is called a crystal lattice. This is a lattice. Something to remember. Let's have a few more examples. If lithium reacts with fluorine, and lithium loses its outer shell electron, gives it to fluorine, so now you have a fluoride ion, 1-, and a lithium ion, plus, 1+. From that, you can work out that the formula of lithium fluoride must be LiF. For every lithium ion, there's a fluoride ion. Slightly more tricky example, magnesium and chlorine. So here, magnesium, to get a full outer shell, it needs to lose 2 electrons now, not 1 electron. So what it does is it gives an electron to each of 2 chlorine atoms, because the chlorine still needs to gain 1. So the chlorine becomes chloride, and the magnesium ion is formed, which is Mg2+, because it's lost 2 electrons. 1 to this chlorine and 1 to this chlorine. So for every magnesium ion, Mg2+, there are 2 chloride ions, so its formula is MgCl2. Right, have a go at the questions on those pages and read the text to get some extra information. You can pause the video for a second. Okay, when you're doing exam questions, almost always you only need to show the outer shell, the valency shell of electrons. So let's have a look at an IGCSE question. You have to draw a diagram that shows the formula of lithium oxide, the charges on the ions, and the arrangement of the valency electrons around the negative ion. So you only have to show the valency electrons around the negative ion. The crosses represent the electrons from oxygen, the dots, electrons from lithium. Now this diagram's got the electrons the wrong way around, but it doesn't matter. So oxygen has got 6 electrons in the outer shell. So to get a full outer shell, it needs to gain 2 electrons. And it does that by taking 1 electron from each of 2 lithium atoms. So this lithium atom gives an electron to the oxygen and becomes a lithium ion. This one does the same. And this now becomes an oxide ion, O2-. It's got 8 electrons in the outer shell. So for every oxide ion, there are 2 lithium ions. This is somebody's diagram, which is quite nice. And it shows the same thing. Notice the lithium here, they haven't put any electrons around the lithium because they're only showing the outer shell. And the same with oxygen. Now technically, 2 of these electrons should be dots and the rest should be crosses, but don't worry too much about that. My point here is that you only need to show, to get the final marks, this, which is the ions and the charges. That should be O2-, and then the formula of the compound to get the 2 marks.